Hello everyone. Welcome to the first section in multivariable calculus. This first section that we are going to be looking at is titled Three-Dimensional Coordinate System. Within the three-dimensional coordinate system, we have three different axes that we now have to account for. The first one being the x-axis, the second one being the y-axis, and the third one being the z-axis. I have a screenshot here from Geogebra to show you what the three-dimensional axis looks like. However, I'm also going to take the liberty and draw this three-dimensional coordinate system. So what I typically start with is my vertical line, and this vertical line will account for my z-axis. So this is going to be z. Then I go ahead and I get my straight edge and I start drawing in my x-axis and then my y-axis. Alright, here's one of them. This one is going to be my x-axis. There we are. And then I'm going to do the same for the y-axis. There we are. So this is how it looks like when I'm looking at my x, y, and z coordinate system. Now, because we have an x, y, and z coordinate system, this actually breaks our space that we're working in into 8 equal parts. And those parts are known as octants. So I'm going to show you a really quick depiction on GeoGebra as to how that's going to play out with the ordered triplets that we are going to be working with. So I'm going to bring up GeoGebra on screen, that way you all can see it. So here's my GeoGebra for my three-dimensional coordinate system. Now, like I said before, the three-dimensional coordinate system is broken up into 8 different portions. And what I have here is that I took the liberty on graphing the planes that go through every single axis. So I have a plane going through the x-axis, I have a plane going through the y-axis, and I have a plane going through the z-axis as well. With that, I took the liberty and I graphed a few points, that way we can see them. Now on our typical x-y coordinate system, as shown on screen, we see that we have 8 different points. I have them labeled as A, B, C, D, E, F, G, and H. Notice that under the x and y coordinate system, we have that points A and B lie in quadrant 1, points C and D lie in quadrant 2, points E and F in quadrant 3, and points G and H lie in quadrant 4. However, this third axis gives us our third dimension view, which means that since point A and B were lying in quadrant 1, it doesn't necessarily mean that they're in the same octant. If you skew the view and if you insert that z-axis, you will see then that points A and B, which are reflected here on my cursor, lie in different octants. Point A lies in octant 1. This is the typical octant that we like to focus on in multivariable. However, the other octants are going to be very beneficial as well. However, most of the problems reference that first octant. Looking at points C and D, they were in quadrant 2 under the x and y coordinate system. However, they lie in different octants because they have different z values. And you can view the ordered triplets for these ordered triplets or these ordered pairs over on the left hand side of my screen. I have here that point C and D, they look very similar, but again they have the different z coordinate. looking at points E and F, once again, they lie in two different octants. Points G and H, again, two different octants. So this is a very nice visual to see that even though in the X and Y coordinate system we had quadrants, we still have something similar moving on into R space 3, otherwise known as 3 space. So once we have this, we can now start talking about distance. Under our normal X and Y coordinate system, we could have a distance that we calculate that would be this line segment that I have made from the origin to point A. Under the X and Y coordinate system, it would be very straightforward to use the distance formula. However, in R space 3, again, we're skewing our view, which means that we're adding a new component to this. And adding a new component to try to find the distance of that line segment is still going to be almost the exact same process as finding the distance in R space 2. So let's go ahead and take a look at that back over on our whiteboard. All right, here we are. So what I'm going to do here is I'm going to write in the distance formula. And this is in R space 2. That distance formula can be written as the distance between point 1 and point 2 is equal to the square root of the sum of the difference, the sum of the square of the difference between the y coordinates and the x coordinates. There we are. Now, a distance in R space 3 looks very, very similar. And if you want to run through a proof of this, your book has a really nice outline as to how the proof actually runs through and how you actually get this formula, which is really nice to see because, again, it looks very, very similar to what we've been working with back when we were working with R space 2. Oops. And this is Z1 minus Z2. So notice the only difference that we really have here is that we're adding this new component, which is going to be the distance that is calculated by that third component, or the difference that's going to be calculated by that third component, which will be the difference in the z values. Now, these distances can be thought of different ways. We could always rewrite this to just be the difference or the magnitude between P1, P2, and the same thing can happen here, the magnitude between P1 and P2. And I use the reference of magnitude because we will be getting to that portion in a few minutes or in the next sections. Now, as far as we're concerned for the ordered triplets, every ordered triplet is going to follow the exact same pattern that we kind of learned back in the rectangular coordinate system. We start from the origin and we move a certain amount in the x direction, whether it be to the positive or the negative side. We move to a certain portion of this, and let's call this A. After we move in that A direction, then we move in the y direction a certain amount. We'll call this B. Then after that, we move a certain amount to a z direction, and we're going to call that C. In doing so, we now create this new point in R space 3, which we're just going to call a point, that has an ordered triplet of A, B, C. And that's going to be where it lands in R space 3. So as we start looking at this, all of the ordered triplets in R space 3 must have three portions to it, or three parts to them: the X component, the Y component, and the Z component. Now, this is kind of nice because if you then start analyzing all of this through your calculus lens, you then start realizing that Calc 1 and Calc 2 were strictly done with the lens of working with only two components, X's and Y's. So that means that in this course, we're actually going to revisit all of those topics, adding this new component, which will be the Z component. And we're going to be able to talk about derivatives, integrals, rate of change, everything that we talked about back in Calc 1 and Calc 2, we are going to be able to revisit. So that's very nice to see. Now, I want to go back into GeoGebra and I want to talk about what the equation of a sphere is. Because in the equation of a sphere, back in R space 2, we actually worked with the distance formula and fixing one of these values, or one of these points. So if y2 and x2 were fixed, meaning they don't move, then we could just call this hk, and then we'd be able to extract the equation of this the circle. So let's talk about the equation of the sphere, and let's do that on GeoGebra. So here we are on GeoGebra, and I went ahead and I inserted the plane here where z is equal to 0. That way we get a certain point of reference when we start viewing these three-dimensional objects. So when we're looking at the equation of a sphere, or more specifically when we're looking at the actual sphere, a sphere looks like a circle if you're looking at this from above, which means we're only looking at this on the X and Y coordinate system. We see that we do have a circle here. Now, the equation to this would then be, well, what's the equation of the circle in R space 2? And that would be, well, the radius or the circle is centered at the origin 0, 0, and it has a radius of 3, which means the equation should be x squared plus y squared is equal to 3. Under the new components that we have, that z component, we see that this sphere still has a radius of 3 no matter where we put that point on the sphere, and that's measured from the origin, which means the new component should have a z component that should be squared. And we can try to verify this by inserting that equation that we saw. So I'm putting in x squared, then I'm going to do plus y squared. If you notice on screen, GeoGebra is trying to anticipate what type of shape I am inserting. Z squared, there we are, and then it's equal, radius is 3, so that means the radius must be 9. Or sorry, it must be equal to 9. Notice the sphere that I just created, the equation of the sphere that I input, is superimposed on the previous sphere that I had already drawn, which was this one here. So we get to see the equation of the sphere, which is kind of nice, and again, that equation of the sphere is based off of that distance formula in R space 3. So let's go through and let's actually formalize this equation of a sphere before we move forward. Here we are. So I'm going to start saying that the equation of a sphere with center HK L with radius R is given by, we're going to have x minus h squared plus y minus k squared plus z minus L squared is equal to r squared, which again looks very, very similar to the equation of a circle in R space 2 minus this third component. So that's really cool to see. Now that we have seen this graphically, let's go ahead and let's talk about this algebraically and see how we're going to be working with that equation of a sphere. All right, so here we go. Here goes the example that we're going to be working with algebraically for the equation of a sphere. So in this example, we want to show that the equation represents a sphere. We also want to find its center and radius. Now, the equation that we're going to be working with here is going to be 3x squared plus 3y squared plus 3z squared is equal to 10 plus 6y plus 12z. There we are. So again, what we want to do is we want to show that this equation represents the equation of a sphere given right up here. So what we're going to do is we're going to start off by completing the square for each individual variable. In order to complete the square for each individual variable, what we have to do is make sure that all of the variables are on one side of the equation. So that's where we're going to start. We're going to have 3x squared, and when you're moving these variables, make sure you match them up term by term. That way you can have all of the like variables together on one side. And here we go, that's 12z is equal to 10. Very nice. Second thing you want to do is you want to go ahead and, in this particular case, because all of the x squareds, y squareds, and z squareds have a factor of 3, you want to go ahead and divide all of the equation by that 3. So I'm going to go ahead and divide every single term by that 3. So I'm going to divide by 3, divide by 3, 3, 3, 3, and finally 3. There we are. So my new equation looks like x squared plus y squared minus 2y plus z squared minus 4z is equal to 10/3. Very nice. Second step at this point in time is going to be to find the b coefficient, or in other words, the coefficient that is multiplying the single variable. So in my first instance here, that's -2, because -2 is multiplying the y term. And then I'm going to identify -4 because it's multiplying the z term. Notice there is no x term in this particular case, no single variable x. So at that particular time, we're just going to leave that alone. And what I'm going to do here is I'm going to identify this -2. And what I'm going to do here is I'm going to take -2 and I'm going to divide it by 2. We always cut it in half, and the result here is going to be -1. Once we get this result, we're going to square that result to get us 1. And this is the number that I'm going to add to both sides of the equation in order for me to accomplish that, completing the square. The next the next coefficient that I'm going to identify is -4. So I'm going to do the exact same process. -4 divided by 2. That's now going to get me -2. Then I square that result. to get me 4. And this is the variable, sorry, this is the term that I add to both sides. So when I'm writing here, I'm going to write x squared plus y squared minus 2y, and then I'm going to insert that value that I found for that coefficient, so that's plus 1. Then I'm going to have plus z squared minus 4z. Again, insert that new variable, sorry, that new term, so plus 4. Oops. Here we go, plus 4 equals, on the right-hand side, we got 10/3. And because on the left-hand side we inserted a 1 and a 4, I'm going to do the exact same thing here. So that's going to be plus 1, and then this other one's going to be plus 4. There we are. Now, we've balanced the equation, so all we need to do now is factor. Now, for the x squareds, it's nice that we don't get to factor here, so we're just going to leave it as is. But for this 3 middle terms, this y squared minus 2y plus 1, this is now a perfect square where we have y minus 1 quantity squared plus the last 3 terms, that's now going to be z minus 2 squared in factored form. And all we have to do is add the very last coefficients. So that's going to be 10/3, and then I'm going to add plus 1 and then plus 4, and that should get me 25 divided by 3. So adding these 3 should get me 25 divided by 3, or in other words, 25/3. Looking good so far. At this point in time, we can now see that this equation is the equation of a sphere. So we're actually done here. This is our final answer. But we also need to identify what is the center and what is the radius. So what I'm going to say here, the center is the order triplet x minus 0, so that's going to be the x coordinate of 0, y minus 1, that means that's going to be my k element, so that's just 1, and then z minus 2, that means L is my element of 2. So the center for this sphere is at 0, 1, 2. The radius in this particular case is going to be the square root of 25 over root 3. Now we can go through the whole process and we can rationalize this. This radius to get us 5 divided by root 3. Or if you want to write it a little bit more cleanly, this is going to be 5 times root 3 divided by 3 as the radius. And there we are. We have the center and we have the radius, all nice, compact, good looking. Great. So you can expect to see something like this either on a quiz or on an exam, just to show that completing the square process. Because at the end of the day, this is going to play an important role once we start our parameterization techniques later on in chapter 16. So let's look at a few more examples that are going to take us in a slightly different direction. And on this example here, we want to describe the sets of points defined by the following conditions. And let's see what we have. Part A, we are going to have x squared plus y squared plus z squared is equal to 4. And we're going to apply a restriction here that y must be greater than or equal to 0. Okay, so kind of keep that in the back of your mind. Part B, we're going to be looking at x minus 3 quantity squared plus y minus 2 quantity squared is equal to 1, and z is going to be greater than or equal to -1. So what I want you to do at this point in time is, if you want to pause the video, I would encourage you to do so and try to get a visualization for what these equations, what these conditions are giving you in R space 3. All right, so again, if you want to take some time, pause the video, I encourage you to do so. All right, so what I'm going to go do is I'm going to go to Geogebra, and I'm going to give you a description on Geogebra, and then we're going to come back and give the actual description here on this page. So follow me along. Here we are on Geogebra. So I have my coordinate system here, my x, y, and z coordinate system. Now, what I'm going to do here really quickly is I'm going to make sure that these coordinate systems are labeled. Whoops, here we go. So we got our x coordinate system, then we're going to have our y coordinate system, and finally our z coordinate system. There we are. So we have our x, y, and z axis. The first equation, part A, was the equation of a sphere. X squared plus y squared plus z squared is equal to 4. It's the equation of a sphere centered at the ordered triplet 0, 0, 0, and it has a radius of 2. But the other restriction that is being applied is that we have y is greater than or equal to 0. So here's my sphere. Awesome. Radius 2. Let's double check. Sure, looks like radius 2. Great. But this has no restriction. So what I'm going to do really quickly is I took the liberty on parametrizing a sphere to get us the view for that added restriction, which is y is greater than or equal to 0. Which means that this sphere will only exist for all the y values that are greater than or equal to 0. Which means that we really have a hemisphere given to us here. It's part of the sphere, and you can see that only the top part, or I should say, only the right side where the y values are greater than or equal to 0 exist for this sphere. And there you are. Looks really neat. So that's for part A. Let's now reimagine part B. So for part B, it kind of looks like a circle. Would you not say? Because we have x minus 3 quantity squared plus y minus 2 quantity squared. So that to me kind of signifies that we have some sort of circle. Let's see, can I get this here? There we go, some sort of circle. I don't want to give it away here. So we have some sort of circle that we are analyzing. All right, that's going to be pretty good. But there is no z component. However, we are adding a restriction for a z component to be any value greater than or equal to -1. Well, if there is no z component, that means that the z component can be whatever it needs to be, which means we have a right circular cylinder here where the ends, meaning the positive z values or the negative z values, are open-ended. They extend forever. However, the added restriction is that z must be greater than or equal to -1. So I want to somehow, some way, cut off this cylinder at -1. Well, oops, I wanted to show you that here, that I superimposed the parametrization for this right circular cylinder beginning at z is equal to -1 and extending all the way upwards. To see it more clear, here is that cylinder. So it definitely ends at -1 for the z values, but it extends upward in the positive z direction indefinitely. Now you can see that this cylinder is shifted over an x value of 3 and a y value of 2 for its center. Follows all those algebraic techniques that we learned back in algebra, which is great. So this is what we're looking at. A right circular cylinder centered at the ordered triplet of 3, 2, and 0, where the cylinder begins at -1 and extends upward in the positive z direction. Now that we have those views, let's go back and let's write them out in our whiteboard page. So follow me along. Here we are. So let's go ahead and let's write this out. Part A, we had a hemisphere, or let's write this. Hemisphere centered at 0, 0, 0 with radius of 2 and y is greater than 0. Awesome. So there's my description for the first part. For the second part, part B, remember we said it was a right circular cylinder. So I'm going to go ahead and write that here. It's a right circular cylinder centered at 3, 2, 0 has a radius of 1 and z is greater than or equal to -1. There we are. So this is what we're looking at, and this is how we're going to be extracting, or how we're going to be putting together what we know from our Cartesian coordinate system, and simply just adding a new axis to this, which is the z-axis. So I hope you all enjoyed this lesson, and I will see you all here for the next lesson on vectors.